So we'll start by trying to get the x by itself. So I'm going to add the 1 over. And then divide the 2 over. And then to cancel out that exponent base of e, I need to use a logarithm. Which logarithm would I need to use to cancel exponent base of e?
Put e on the other side.
I do not do that. I need to use log base e, otherwise known as the natural log. And then the natural log cancels out the exponent base of e. And then I just subtract the 4 over and then swap the x's and y's. Anybody else? Amanda? Back in the time machine, huh? Let's see here. Radioactive decay. When radioactive atom decays, it breaks into a new lighter stable element and emits a particle. The rate at which radioactive elements decay is called a half-life, which describes the length of time needed for half of the radioactive sample to decay into a different substance. Carbon-14 is a radioactive isotope of the element carbon. It is known that carbon-14 has a half-life of 5,730 years. Suppose you have a 100-gram sample of carbon-14. How much carbon-14 would remain 25,000 years later? So I'm going to use my continuous model here. So my initial amount is 100. That's the grams of carbon-14 I have. My value for R, because we're talking about a half-life, is negative 0.5. Since it's decay, it needs to be decay. The decay values are less than 1 or less than 0. So that's negative 0.5 T. And the way we've written this, T is going to represent the number of half-lives. So what I need to plug in for T is how many half-lives is 25,000 years. That would be 25,000 divided by 5,730. Okay with that? Because each half-life you decrease by half. So that's what I'm going to type into my calculator for part A. I know you asked about part B, but we kind of need to at least feel okay about part A before we can do part B. 1,000. So about 11.3 grams would be the answer for part A. It is known that the ratio of carbon-14 to carbon-12 in living organisms is 1 to, I don't know, what's that, a trillion? Once a living organism dies, that ratio begins to decrease because of the radioactive decay of carbon-14. Scientists can measure this ratio in dead organisms to figure out when the organism died. You are presented with a document which purports to contain the recollections of a Mycenaean soldier during the Trojan War. The city of Troy was destroyed in about 1250 BC, or about 3,250 years ago. Carbon dating evaluates the ratio of carbon-14 to carbon-12. Given the amount of carbon-12 measured, or given the amount of carbon-12 contained a measured sample cut from the document, there would have been 1.3 times 10 to the negative 12 grams of carbon-14 in the sample when the parchment was new, assuming the proposed age is correct. According to your equipment, there remains 1.0 times 10 to the negative 12 grams. Is there a possibility that this is a genuine document, or is this instead a forgery? Okay. So what we're wanting to do is we need to decide, is this number indicating that that the document is around that age, or older would be okay also. Again, you can't forge something that hasn't happened. But if it's much newer than that, you know, it's not that old, that would be our indication that it's a forgery. Okay. So, this is our initial amount of carbon-14. And this one is our future amount. So I'm going to set that equation up to solve. I'm going to do this graphically. Is how we've been doing this. That's kind of a gross number, but I guess it's going to be fine. We can make it work. So I have 1 times 10 to the negative 12, and then 1.3 times 10 to the negative 12 times e to the negative 0.5 times x. And I'm going to set my window. So again, x is representing time. This thing should come out to be a little over 3,000 years old. But the t I have here is actually a half-life, is 1 half-life. And I know the half-life for carbon-14 is 5,000 something. So I'm really just going to go from like 0 to 1 here. I think when I find this, I'm going to get some fraction of a half-life. Hopefully something a little bit more than half is what it looks like. But we'll see. Go back once maybe. The minimum value I can have is 0, right, since it's a decay. The maximum is this 1.3 times 10 to the negative 12. And go up by 1 times 10 to the negative 13. So basically we'll get like 13 of those little tickies in there. We'll set a window now. Oh, we just set our window. Sorry, we'll draw a graph. So there's my sample. There's what I got for the intersection. So second, trace, intersect command, enter, 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 and I get 0.52, let's say 0.525. What's going on? Where's, oh boy. T is about 0.525 half-lives. Right? So I'm going to take that number then and convert it into years by multiplying it by the length of my half-life, which is 5,730. So that's 3,008 years. And I would conclude that that's likely, depending on, assuming that this instrument we have has like, you know, is giving me a pretty accurate measurement, which I don't know how precise these instruments are, but given what we did here, I would say that it's like, you know, it's possible that this thing is a forgery, although it's a pretty recent forgery. It's within 200 years of when I think that the event would have been taking place. It's a relative recent forgery, but it's at least a couple generations removed, presuming that our instrument is really accurate. Oftentimes when you do this sort of thing, it'll give you a range of values. You know, like it's between, you know, 3,000 and, you know, 3,200 years old or something. It would give you a range of values, I think, when I've seen carbon datings done. The way they report things is because you're not giving perfect, like a perfect measurement. You're given like an upper and lower bound for how much was actually measured. Since the amounts are awfully small, as you're seeing. But yeah, that's the gist of it. It was basically just like one of these graphing problems. There's just a lot of words there kind of describing what was going on, and the numbers were kind of kooky. And then you had to deal with, if you did set it up correctly, taking a look at that value for t and understanding that that's representing an amount of half-life and not years, because if it's years, it makes little sense. Wait a minute, it's half a year old? That doesn't make a lot of sense, but if you're going, oh, it's half a half-life. Okay, well that's about 3,000 years. That's pretty old still, but not quite old enough, I think. Does that help? So there's a couple of places where you could have like kind of gotten stuck. If you missed that the R needs to be negative, easy to make that mistake, missing that it's a decay and it needs to be negative. Little hope to resolve the problem correctly at that point if you missed that. If you did catch that, then getting hung up on the t being half-lives rather than years, again, would have needed to think a little bit about what's going on there. But if you missed that idea, again, your answers make little sense. But if you did both of those two things, you should have been able to kind of get to the end there relatively easily. As it wasn't so bad, it took me as long to read it as it did to actually set it up and do it. This is a lot of words. Does that feel okay though? Okay. Cool. Any other questions before we move on?
Can you do number of times on the homoplot?
this is same idea as number 9. So again, we're just going to isolate the x. So I'd start by subtracting the 8 over. And then we need to divide both sides by 2. And then what is going to cancel this log here out front? So we need to use an exponent base to cancel this. What exponent base would we need to use for this one? What is the base on that logarithm? Not 1. This is the common logarithm. This is log base 10. So there's no base written. That is the common logarithm. And then we just add the 5 over and swap the x's and y's. Oh, yeah, that's a 3. Shows how messy my penmanship is. Turned into a 5 on my paper.
Nothing from the logarithm that's going to be done.
Not in front. The base is here.
Yeah. If there's no base, how it's going to be done?
Yes. That's the common logarithm. I think last time we defined that right here. Mackenzie? 13. Sure. Obviously, that's got to be from worksheet 3 because the other one, all the other worksheets were like 4 or 5 problems, right? Okay. So the tricky part here is what the heck do I do with this number 1? I'm going to refer back to the previous lecture. So we add these additional asides. The one that I'm going to be particularly interested in is this one. So I'm going to use that little trick. So I'm going to start first by rewriting 1 as log of e, or natural log of e, I guess I should say. Is that okay? And then I would just proceed in the usual fashion, so doing power, product, then quotient. So I do powers next, and I move that 7 inside my logarithm to the exponent. And then do my products, so the addition turns into multiplication. And then I do my quotient, and that subtraction turns into division. Does that feel okay, Mackenzie? I want to make a little aside. It's a mistake I see students make frequently. Note that this is not the same thing as this. I see oftentimes students writing with multiple logs still in their answer. When you're compressing, there should only be one logarithm left in your final answer. Okay with that? Again, it's something where it's fairly easy to make that oopsie. I want to caution you against it right now. That those mean different things and they're not equal. Last call on questions here before we start the new stuff for today. Okay. Let's do it then. So today I want to talk about solving problems. And I want to just refer back to this idea that we talked about last time that I'm just going to refresh our memory on, because it's the most important idea that we're going to be taking advantage of while doing these solving problems. And we talked about it last week, and it's been a weekend and stuff fades. And it's this idea that the exponent base of b cancels logarithm base b, and that logarithm base b cancels exponent base b. So this is the kind of the key idea that we're going to be using over and over and over in almost all of these solving problems. We're going to look at today. So again, this is an idea that we talked about last time. It's in our notes from last time, but we're going to be using it frequently today. So I just wanted to make sure to restate it, kind of say what it means again. Just like division cancels out multiplication or multiplication cancels out division. Same kind of notion here. So we're going to start with some exponential equations. So an exponential equation means that the variable is in the exponent, right? Everybody's okay with that? And I'm just going to run through some examples of a couple of different types of exponential equations that I think are reasonable for us to solve given what we've done so far this year. And then we'll look at some logarithmic equations. Similar situation. Okay? And that's kind of all I'm going to have planned for today. So let's say we have something that looks like this. What should be the first thing that I want to do? Add. That's correct. And I'm going to ask you guys for a lot of input here today, because I think that in particular with these solving things, I want to kind of help develop your intuition about what to do and what you can't do. So I'm really going to be interested in kind of hearing your ideas, and it's okay if you're wrong about something, because those are things that I want to make sure that we correct and remove that as something that you want to do in that case, rather than just having me bulldoze through on how to do these. You know what I mean? I won't let us write down anything wrong without telling us what I'm doing right now is going to be wrong, kind of thing, just as if it's one of those things that's worth kind of pointing out why it's wrong. But for the most part, I'll explain and just ask for something, another idea. But it's okay to make wrong ideas. In fact, it's encouraged. Like, that's how we learn, right? Why do we fall down, Bruce? So we can learn to stand back up. For all my Batman fans out there. Okay. What's next? We want to divide by 5, right? We want to isolate the exponential piece. So we want to get rid of that coefficient there. Can I multiply the 5 and the 3 together? Is that ever going to be okay to do? No. The reason is it would be violating one of our properties of exponents. Remember the 2 ways that we can multiply exponentials together is if the bases are the same, we can add their exponents. Or if the exponents are the same, we can multiply their bases. But in that case, both the base is different, 5 and 3, and the exponents are different, 1 and then 2x plus 5. So you can't do anything with those as far as combining them together. Everybody's clear as to why? Again, that's a common mistake I see students make, is to just go ahead and call that 15 to the whatever. Don't want to do that. Okay, so we've isolated the exponential part. What should we do next?
Get x by itself.
Get x by itself. Great. So we have to cancel out that exponent base of 3. How do I cancel that out? Log base 3. And we'll do that to both sides. So one thing worth pointing out here is that I have to, when I'm doing this log to both sides, it has to be to the entire side. It can't be term by term. Right? Just like when we square both sides, we can't just square term by term. We have to square the entire side. Okay. So log base 3 of 3 to the 2x plus 5, what does that equal? Or what does that reduce to? Yeah, just 2x plus 5. Great. And what's log base 3 of 3? 1. Now, when I take the logarithm of a number, is it frequently just going to be a whole number like that? No. Oftentimes, it's going to be an irrational number. Well, the next example, that'll be the case, and we'll talk about how to write an exact answer when that comes up and what that exact answer would look like. But this one, it evaluates down to a whole number, and we'll do that. Everybody's okay? And then from here, it should be easy, right? We can subtract 5 and then divide by 2 to get negative 2. And I skipped writing down those 2 steps. I hope everybody's okay with that. At this point, that's like a pre-algebra problem, right? And I'm hoping we were pretty good with those. What does this remind us of? This is pretty similar to finding the inverse that we did in the last homework, right? The procedure feels very similar. We have yet to get into the ones where we have to be kind of sneaky. But let's do another, just to make sure that we kind of got it. sorry, I'm going to make that sorry, I wanted this to have an answer. I was going to get into some trouble there. Okay, first thing I would want to do is, yes, sir. And the next thing I would do is?
Divide 10 by 3 over 2.
Okay. Instead of thinking about it as division, I'm going to think about it as multiplying by the reciprocal, but it's the same thing. Everybody's good there? That regardless, you're doing the same action there, whether you think about it as division or multiplication. I just like doing it as multiplication because it's easier to do with my head. Because I want to keep the fraction if I can. I'd rather not have it be a decimal because we're looking for an exact answer. So I don't want to get a decimal that I might have to round. Right? If I divide by 3, I'm going to get a repeating decimal, and I don't want that. Everybody's okay still? Okay. Next up would be?
10 divided log 7.
Okay, so we're not multiplying because log isn't a number, but we're going to take the log base 7 of both sides. I knew what you meant. I'm just clarifying for everybody else that this is not multiplication that we're doing here. But that's okay. I knew what you meant. Now log base 7 of 20 over 3, is that going to simplify? Definitely not, because no part of it has a factor of 7 going on in there, right? You agree? So that's going to be a bunch of nothing. So I'm just going to leave it. Oops. The way it is. So that is some big gross decimal. It's an irrational number. I'm not really interested in writing that irrational number down. I'm just going to leave it the way it is. So my last step would be to subtract 5 and then divide by -1, right? Everybody agree? So when I do that, this is how I would write my exact answer. After I subtract the 5 over and then divide by -1. The dividing by -1 switched the signs. That's why the 5 is positive now and the logarithm's negative. Everybody can see that? And then if I wanted to, depending on what the directions asked for, maybe it asked you to also round your answer to like 3 decimal places or something. Now I would get my calculator out and type this in if I wanted a rounded answer. So I can do 5 minus. And then to get the log base 7, we press the math button. And we go all the way down to the bottom of the list and we look for the log base option. We type 7 in the base. And then do 20 divided by 3. And so we could write that as like 4.021 if I was asking for a rounded answer. I'm not going to write that down right now, but if you wanted, or if I was, the directions asked for rounded answers, that's how you would get it. Please wait till the very end before you do any rounding. Because I want to point out too, if we said 20/3 is, if you wrote that as like 6.7 instead of 20/3, like you rounded there because you're like, oh, it doesn't matter, I'm just going to, I'm going to round it anyway, so I just round all the time. Like you get a little bit different of an answer, and depending on what the base of the logarithm is, maybe that makes a big difference and maybe it doesn't. So just be careful about that. Try not to round more than one time in a problem. You'd really like to round only one time at the very, very end.
Can you just explain how you got like the log 7 part?
Yeah. So I need to cancel out.
Like how you got like on the calculator.
Oh, on the
Like,
calculator.
Yeah.
Sure. So I press the math button, and then I scrolled all the way down to the bottom, or I just press the up arrow to go to the wrap around to the bottom. And you should see the log base option.
Oh, thank you.
You see it?
Yep.
And then you just press enter, and it pastes it on the home screen. You put the number where you want the base, or whatever number you want in the base. Yeah, no problem. We feel okay about this situation? Let's see. What do you want to do on this one? Yes, ma'am?
We need to go straight to taking the log out of 3.
Sure.
Or
We can do log base 3 of both sides to start. Sure. That would be okay. There's another way you could approach this also, but we'll circle back to that after we've gone down this road. You could do this one actually without using a logarithm. But we'll talk about how you would go about doing that here in a second. It's not necessary to do it that way, but I wanted to point out that it is also possible. Everybody's cool with what we did here first? Now, log base 3 of 27 is something that we can do. You could do that in your head, or if you really wanted to, you could break out your graphing calculator and just type that in. You might notice that 1 over 27 is 3 to the negative 3. Or if you typed it in your calculator, you'd get negative 3 to come out. It's not necessary that you do it by hand. But you could. We subtract the 2 over and then divide by negative 1 to get 5.
do we need to show them?
I did. I mean, like, once you get to that step, if you do it correctly.
I kind of passed no
Yeah,
idea.
I mean, like, whatever. I need to see some of the beginning algebra, but when you get down to, like, this is an algebra 1 problem now, whatever. Don't make any mistakes, though, because if you make a mistake and I can't see what it was, you could get a bigger deduction than if it's just like a little, oh, look at that, you added 4 instead of 5 or something. But I can see what happened. So I promised you there was another way you could think about this. And that would be noticing that 1 over 27 is also a power of 3. And the only way that this can be equal is if the exponents are equal, right? So you could do it that way without having to use a logarithm. Right? If I have 3 to some power equal to 3 to some power, the only way that those things can be equal is if the powers are the same. You guys agree with that? So you could do it that way also. That's maybe a little bit quicker, but, you know, it's also different. And if you catch that or not, sometimes it's tough to see, oh yeah, I could have done that. Whatever. Okay. How about how is this one different than the ones we've seen previously?
Because we have two that have powers too.
Okay, so we have two terms that have powers of x, right? Okay, so that's definitely different. Can I do any like adding or subtracting here to combine like terms?
Could you? Well, the exponents are the same, so could you times them?
Well, they're not being multiplied together. Right? The symbol between them is subtraction. Yeah. What do you guys think? Any ideas? What if I told you this is really a quadratic equation? Let me show you how. So 4, I notice, is 2 squared, right? Everybody agree with that? And when I have an exponent of an exponent, like 2 squared to the x, those exponents multiply, right? And I can multiply them in any order I want, right? So that means I could switch the locations of those exponents if I wanted to. So I could say that. Everybody okay with that notion? So now I have something squared minus that same something to the first plus a constant equal to 0. So if you can't see that as a quadratic, the other thing you could do is you could just make like a little substitution and replace the 2 to the x's with a y. And then it should be really easy to see that this is quadratic, right? So how would you like to solve this quadratic? What are the different ways we have to solve a quadratic? Factoring or the quadratic formula, basically, right? This one factors, though, doesn't it? What multiplies to give us positive 6 and adds to give us negative 5?
-2 and -3.
Negative 2 and negative 3. So when I solve this, I get y equals 2 and y equals 3. But remember, we don't want to solve for y. We want to be solving for x. So let's go ahead and put the 2 to the x back in. Everybody's okay here? Now the first one we could solve without a logarithm because the bases match. So x just would have to be 1 there. Now you could take the log base 2 to both sides. It's not wrong to do that, but again, I don't think you need to, so I'm not gonna. You know what I mean? And the other one, though, we do have to take log base 2 to both sides. So those are my 2 solutions. You guys want to do another one? Let's do another one like that. What letter am I on? Am I E. Let's come up with a good one. Let's do oh, that's equals something. Nah. Okay. What do you guys think? Do it the same way as the previous one? Here's the question, though. 16 and 4? Should you write it as like 4 to the x squared and 4 to the x to the first? Or do you want to do 2 to the x to the fourth and 2 to the x squared?
The first
The first one. Do you think it matters?
one. That one just, I feel like it's going to be less math because we already have another 4x.
I would leave it at 4 squared so that way you can
Okay. Let's just see, right? So I shortcutted through a couple of steps there to write these this way. Is everybody okay with what I shortcutted through? It was just moving some exponents around, right? We talked about how we can do that. I don't need you to show me doing that. Show doing that on your papers if you just do it. That's fine. I'm going to write both of them down, and we'll do both of them at the same time and just kind of see how it goes and see if it does make a difference, right? They should both give me the same answer, you'd think. But they kind of get there in different ways, and it gives me an opportunity to talk about something that can happen that I like. It's probably worth talking about. Okay. So make a substitution. Is that how you guys would prefer doing it? Is it easier to see the factoring with the substitution? So far, so good. So again, on the left, we're left with this quadratic, right? Does that factor? Okay, what does it factor to?
-4 and -1.
Good. Again, you could use the quadratic formula there, but if it factors, I'd much rather do that personally than use the quadratic formula. I think it's a little bit less ungainly. So I do the same thing. And then I put back my y, or put back my x's, I guess I should say. Remember, any log of 1 is 0. That's how I got the 0 there at the end. Again, we mentioned that last time, I think. Yep. Everybody's okay with what we did there? Let's go look at the other one now and see if we get the same answer. So this, y to the 4th minus 5y squared plus 4, isn't quadratic, right? Because it has an x or has a y to the 4th. But it's in that quadratic form. This was something that we learned how to factor already. You guys remember doing that? That we can factor this just as y to the squared minus 4 and y squared minus 1. Everybody's okay with that? Remember doing that? Again, if you wanted to do that with a substitution, you're welcome to, and do like z equals y squared or something, but that seems like a little bit overkill to me. But I notice these are both differences of two squares, so they factor. Uh-oh. Seems like this way is giving me more answers, at least right now, doesn't it? Better put our x's back. So far, so good. So this one gives me 0. I'm sorry, that one gives me 1, and that one gives me 0. Just like we had before. So those ones match. But I have these extra 2. How would I solve 2dx equals negative 2? Okay. So you say x is equal to log base 2 of negative 2. What's log base 2 of negative 2 give us? Yeah, it's not defined, right? It's not. So, we can just write like not real here or something, cross it out, whatever. Remember, we can't take the logarithm of a non-negative number. So we do indeed get the exact same things, which is fine. That's good. We should have. We had these 2 extra pieces that didn't work out, didn't give us anything, but that's okay. Everybody okay with that? And that's like the hardest version of these exponentials, is the ones that look like quadratics like this. That's as hard as I'd ask you to do. Everybody's okay? So let's look at some logarithmic equations. Come in. What's going on, Jess? Thanks. Kaylee. It's for you. Do you want to move to Iowa? They want you, it looks like. All right. Let's just do some examples. and we'll just do as many of these as we can. We probably will run out of time before we get to the hardest ones. We'll just pick those up next time. That's not a big deal. Okay? But we're getting short here. Maybe we'll finish anyways. I don't know. We'll find out. What should I do first? Add 4 to both sides. Lovely. Then what? Good. Then what? How am I going to get rid of that logarithm out front? Excellent. So I'm going to use the exponent base 10. And again, I am going to write my 10 like kind of absurdly oversized so that I can't accidentally mistake it for multiplying by 10, at least initially, yes. What's the base on the logarithm? When there's no number written there, it is base 10. So I use the base to match the logarithms. Right, we had mentioned that here yesterday. So these two special logs. Log with no base is log base 10, and log ln is log base e. So again, 2 of those little abbreviations that you gotta make sure we remember. But that's why we're doing the examples, right? So we have a chance to do that. So that's gonna cancel out. And I'm going to be left with a square. And then I could type in 10 to the 4th. That's a 10 with 4 zeros after it. And then I can just subtract 3 and divide by 5. Right? One thing we have to be careful of, though, with the logarithmic equations is we can get extraneous solutions. Oh, great. But here's the check. All I need to do is make sure that my value for x is still, or inside the logarithm, is non-negative. So 5 times this number plus 3, definitely non-negative, right? So it has to be greater than 0. As long as it's greater than 0 and you plug it back into the logarithm, it should be fine. You don't have to actually grind out the whole check. Is that okay with everybody? Obviously, you could grind out the whole check. It wouldn't be wrong to do so. But I'm just trying to save you a few minutes here and there. You know what I mean? You can eyeball check them, that's best. Right? Very similar to back when we solved the rational equations, where all you have to do is check to make sure the answer didn't give you gave you a zero denominator. Very similar to that situation. Oh, goodness gracious. Excuse me. Well, let's just go ahead and do this. Oh no! What's wrong with this one? I got two logarithms in the problem that both have an x in it, right? What do I need to do? What should I do first? What's that? That's the greatest idea I've ever heard. Yeah, so Amanda says, what if I take this side here and I compress it into a single logarithm. And if you wanted to, you could distribute that x through. We'll have to do that at some point. I guess we might as well do it now. Everybody's okay? What next? Yeah, so now we got to get rid of that logarithm. Now that we have just a single logarithm, the left-hand side is just one logarithm. Now we can use that exponent base e to both sides. Again, I'm going to draw it absurdly large.
Why is it E?
Why is it e?
Special log.
Yeah, what's the base of natural log? It's base e.
Oh, and that's okay.
Again, that was one of these
Yeah.
special ones from last time. There they are. So again, got to remember that notation. It's going to be super important. We get that memorized. Okay. So that gives me x squared plus 3x equals e to the fourth. How am I going to solve that? Well, it's a quadratic equation, right? So I'm going to move it all onto one side. With that stupid e to the fourth there, there's no way that's factorable. So what do I have to do? Quadratic formula. So -3 plus or minus square root -3 squared, or sorry, 3 squared is 9. So minus 4 times 1 times negative e to the fourth is plus 4e to the fourth over 2. So one answer is 6 and change. And then if we subtract, the other is -9 and change. Is that right? Oh, 3/4. Not close. But I'm not done, because I didn't check. So go all the way back to the beginning. If I plug 6 in for x, that's good. If I plug 6 into x plus 3, that's good. But if I plug negative 9 in for x, remember when I'm checking, I'm just making sure that when I plug the x's back in, they have to be non-negative. So this guy would have been my extraneous. And I think looking at the time, that was probably the last example that we have time for. Which is okay, because that was the hardest set, or hardest kind of log problem that I wanted to talk about today. If you check back